Welcome to Dormant Knowledge. I'm your host, Deb, and this is the podcast where you'll learn something fascinating while gently drifting off to sleep. Our goal is simple: to share interesting stories and ideas in a way that's engaging enough to capture your attention, but delivered at a pace that helps your mind relax and unwind. Whether you make it to the end or drift away somewhere in the middle, you'll hopefully absorb some knowledge along the way. Tonight, we're exploring the fascinating to some of us anyway, world of calculus and the controversial story of its origins. So, settle in, get comfortable, and let's begin our journey into the mathematical past. So, calculus, that math class you probably struggled through in high school or college? Yeah, that calculus. But have you ever wondered where it actually came from? I mean, someone had to come up with those derivatives and integrals and limits that tortured you during finals week, right? Well, tonight, we're going to look at what historians call the priority dispute between two brilliant 17th century minds, Sir Isaac Newton of England and Gottfried Wilhelm Leibniz of Germany. Actually, Germany wasn't a unified country then, so Leibniz was technically from the electorate of Saxony within the Holy Roman Empire. But anyway, let's start with Newton, born in 1642, or wait, was it 1643? Actually, there's this whole thing with the Julian and Gregorian calendars, and you know what, let's just say he was born in the early 1640s. Newton began developing his mathematical ideas around 1665 when Cambridge University closed due to the Great Plague, and he returned to his mother's home in Woolsthorpe. During what he later called his annus mirabilis, or miracle year, though it was actually closer to 2 years, Newton laid the groundwork for what he called his method of fluxions. And this is where it gets a bit technical, so bear with me. Newton conceptualized changing quantities as fluents and their rates of change as fluxions. He denoted the fluxion of a quantity x as x dot. That's the letter x with a little dot on top. This notation was honestly not the most intuitive, which becomes important later in our story. Newton was primarily interested in the physics applications of calculus, specifically how to describe motion mathematically. He was trying to solve questions like, if I know the position of an object at any time, how do I find its velocity? Or conversely, if I know the velocity at any time, how do I find its position? What's really interesting, and this is something they don't usually emphasize in calc class, is that Newton didn't really think of his work as creating a new branch of mathematics at first. He was just developing tools to solve physics problems. And I should mention that Newton didn't actually use the term calculus for his work. That came later. Oh, and here's a fun fact. Newton wrote about his method of fluxions in a manuscript called De Methodis Searum et Fluxionum around 1671. And this is crucial to the later controversy, he didn't publish it until much later. Newton was actually kind of notorious for not publishing his work promptly. He had this, perfectionist streak. Plus, he really hated controversy and criticism. Meanwhile, across the English Channel, Gottfried Wilhelm Leibniz was independently working on similar mathematical concepts. Leibniz was this incredible polymath. He worked in philosophy, law, diplomacy, and invented an early calculating machine, among other things. But for our purposes tonight, we're interested in his mathematical work. Leibniz began serious work on calculus around 1675, about a decade after Newton, but, and this is the key point in the priority dispute, Leibniz published his first work in 1684 in a paper with the extremely catchy title Nova Methodus Pro Maximus et Minimus in the journal Acta Eruditorum. Now, Leibniz's approach was a bit different from Newton's. Where Newton was primarily motivated by physics, Leibniz came at it from a more abstract philosophical angle. He was interested in developing a general method for dealing with mathematical problems. And the notation, this is where things get really exciting. Leibniz developed the notation that we mostly still use today, the elongated s that represents an integral, s, which was based on the Latin word summa for sum, and the dx/dt type notation for derivatives that's now standard in calculus textbooks worldwide. So I guess we should talk a bit about what calculus actually is, right? I mean, some of you might be completely unfamiliar with it, while others might be having flashbacks to those dreaded exams. At its core, calculus is concerned with change and motion. It's divided into two main branches: differential calculus, which studies rates of change, and integral calculus, which studies accumulation, or the area under curves. Before calculus, mathematicians had been struggling with several major problems. They could find the slope of a straight line easily enough, but what about the slope of a curve at a specific point? They could calculate the area of simple shapes like squares and triangles, but what about the area under a curved line? These were the kinds of questions that both Newton and Leibniz were trying to solve, albeit from different angles. The fundamental insight of calculus is that if you break down change into infinitely small pieces, patterns emerge that allow you to calculate things that were previously incalculable. It's like trying to measure the distance of a winding river. From far away, you might make a rough estimate by drawing a straight line from start to finish, but as you zoom in more and more, breaking the river into smaller and smaller straight segments, your measurement becomes more and more accurate. Calculus essentially takes this process to its logical extreme. Let's get into the specifics of Newton's approach. His method of fluxions was based on what he called moments, infinitely small increments in the fluent quantities. If we have a quantity x, then its fluxion, x dot, represents its rate of change. So if x represents position, x dot represents velocity, and x double dot, the second fluxion, represents acceleration. This is the letter x with two dots on top. Newton's approach was geometric and somewhat intuitive. He thought of these infinitesimally small quantities as ultimately vanishing, which is a bit philosophically problematic, but worked well enough in practice. He developed rules for manipulating these quantities that allowed him to solve a wide range of problems in physics and mathematics. Excuse me. Where was I? Right. Newton's approach. So Newton applied his method to various problems, including calculating the area under curves, finding tangent lines to curves, and analyzing the motion of objects. His most famous work, the Principia Mathematica, published in 1687, used this mathematical framework to develop his laws of motion and universal gravitation. But interestingly, Newton was somewhat reticent about explicitly using his method of fluxions in the Principia. He often presented his results using more traditional geometric methods, even though he had likely discovered them using his new techniques. This was partly because he was concerned about potential criticism of the logical foundations of his method, which, to be fair, weren't entirely rigorous by modern standards. Now, let's turn to Leibniz's approach in more detail. Leibniz conceived of his calculus in terms of differences, infinitely small differences that he called differentials. For a quantity x, its differential dx represented an infinitely small change in x. The ratio of differentials, like dy by dx, represented the rate of change of y with respect to x. Leibniz's notation was incredibly powerful, and that's not something you usually hear about notation, is it? But it's true. His notation made it much easier to manipulate and work with calculus concepts. It clearly showed which variables were being differentiated with respect to which others, and it suggested the reversibility of differentiation and integration. One of Leibniz's key insights was the fundamental theorem of calculus, which essentially shows that differentiation and integration are inverse operations. This is the same insight that Newton had, but Leibniz's notation made it more transparent, I suppose. So now we come to the controversial part, the priority dispute. Who really invented calculus first? This question led to one of the most bitter scientific controversies in history, and actually had long-lasting effects on the development of mathematics in England and continental Europe. The basic facts are clear. Newton developed his method of fluxions first, starting around 1665 to 1666, but didn't publish his work until much later. Leibniz began his work later, around 1675, but published first in 1684 and 1686. The dispute began in earnest around 1699 when members of the Royal Society in London accused Leibniz of plagiarizing Newton's unpublished work. Leibniz had visited London in 1676 and may have seen some of Newton's unpublished manuscripts or corresponded with people who were familiar with Newton's work. The controversy escalated quickly. In 1711, the Royal Society formed a committee to investigate the matter, which sounds reasonable enough until you realize that Newton himself was the president of the Royal Society at the time. Unsurprisingly, the committee concluded that Newton was the first inventor of calculus and implied that Leibniz was a plagiarist. The report titled Commercium, excuse me, my Latin's a little rusty, Commercium Epistolicum, was published in 1712, and Leibniz spent the remaining years of his life defending his reputation. He died in 1716, essentially in intellectual disgrace, which is really quite sad when you think about it. Modern historians generally agree that both Newton and Leibniz developed calculus independently. There's no convincing evidence that Leibniz plagiarized from Newton, though he may have been influenced by some general ideas that were circulating in mathematical circles at the time. The notation and approaches of the two men were different enough to suggest independent development. And, in a way, this makes the whole controversy even more tragic. Two brilliant minds happened to be working on similar problems at roughly the same time and came up with similar solutions, which is actually not that uncommon in the history of science and mathematics. But instead of celebrating this remarkable convergence, the scientific community of the time was divided by nationalism and personal loyalties. Let's talk a bit about the broader context of mathematics in the 17th century, because I think that helps us understand how both Newton and Leibniz could have independently developed such similar ideas. The 17th century was a period of remarkable mathematical innovation. Mathematicians like René Descartes had recently developed analytical geometry, which allowed geometric problems to be solved using algebraic methods. This was a huge conceptual breakthrough that paved the way for calculus. Also, various mathematicians had been working on problems that we would now recognize as calculus problems, finding tangent lines to curves, calculating areas under curves, determining maxima and minima of functions. Pierre de Fermat, for instance, had developed methods of finding the maximum and minimum values of algebraic expressions, and Blaise Pascal and John Wallis had made progress on calculating areas under curves. So, in a sense, calculus was in the air, so to speak. The mathematical community was converging on these ideas from various directions. Newton and Leibniz were the ones who synthesized these approaches into a coherent framework and developed general methods that could be applied to a wide range of problems. But despite the similar mathematical content, there were important differences in how Newton and Leibniz conceived of calculus, and these differences had significant implications for the subsequent development of mathematics. Newton's approach was more geometric and physical. He thought of quantities as being generated by continuous motion, hence terms like fluent and fluxion. His primary interest was in applying these methods to physical problems. Leibniz, on the other hand, had a more algebraic and formal approach. He was interested in developing a general symbolic language for mathematics, what he called a characteristica universalis, or universal characteristic. His calculus notation was part of this broader project. These different perspectives influenced how calculus developed in different parts of Europe. In England, mathematicians followed Newton's more geometric approach and notation, while on the continent they adopted Leibniz's more algebraic style and notation. And it's worth noting that the continental approach turned out to be more fruitful in the long run. The development of calculus and mathematical analysis proceeded more rapidly in places like France, Switzerland, and the German states than in England during the 18th century. Mathematicians like the Bernoulli brothers, Leonhard Euler, and Joseph Louis Lagrange built on Leibniz's work and developed calculus into a powerful tool for solving a wide range of problems. Meanwhile, in England, the insistence of using Newton's notation and methods, partly out of national pride, actually hindered mathematical progress to some extent. It wasn't until the 19th century that British mathematicians fully engaged with the developments that had occurred on the continent. So, let's talk about some of the specific mathematical concepts that both Newton and Leibniz developed. One of the key ideas in calculus is the derivative, which represents the rate of change of a function. In Newton's notation, if y is a function of x, then the derivative is written as y dot. In Leibniz's notation, it's dy by dx. Both men developed rules for calculating derivatives of various functions. For instance, they both discovered the rule which states that if f of x equals x to the nth power, then the derivative f prime of x equals n times x to the quantity n minus 1. They also developed methods for finding derivatives of sums, products, quotients, and compositions of functions. The other main branch of calculus is integral calculus, which deals with finding areas under curves. In Newton's approach, this was conceived as the inverse problem of finding a fluent given its fluxion. In Leibniz's approach, it was finding the sum, or integral, of infinitely many infinitesimal quantities. Both men discovered what we now call the fundamental theorem of calculus, which establishes the relationship between differentiation and integration. Essentially, it says that if big f of x is an antiderivative of f of x, that is, if big f prime of x equals f of x, then the integral of f of x from a to b is equal to big F of b minus big F of a. This theorem is incredibly powerful because it allows us to calculate integrals by finding antiderivatives rather than by directly summing infinitesimal quantities, which would be, well, impossible in most cases. You know, it's interesting to think about how both Newton and Leibniz would have worked out these ideas without modern mathematical notation or computational tools. They were essentially creating new mathematical language and concepts from scratch. For instance, Newton's development of the binomial theorem, which allows us to expand expressions like quantity a plus b to the nth power for any rational exponent n, was a crucial step in his development of calculus. He used infinite series to represent functions and then manipulated these series to find derivatives and integrals. Leibniz, meanwhile, was fascinated by patterns in numbers and developed methods for summing series that led him toward the concept of integration. He also had a deep interest in formal logic and symbolic representation, which influenced his development of calculus notation. Both men were working at the frontiers of what was mathematically possible at the time, often with limited precedent to guide them. It's really quite remarkable that they were able to develop such powerful methods with the tools available to them. Oh, boy, excuse me. Let's talk about the applications of calculus, because I think this helps us appreciate why the development of this branch of mathematics was so important. Newton primarily developed calculus to solve problems in physics, particularly in dynamics and astronomy. His laws of motion and universal gravitation required calculus to express and apply. For example, if you want to calculate the path of a planet around the sun, you need to solve a differential equation that relates the planet's acceleration to the gravitational force acting on it. Without calculus, this would be essentially impossible. Leibniz was more interested in abstract mathematical problems, but he also recognized the potential applications of calculus in various fields. He used calculus to study curves and to solve optimization problems, finding the maximum or minimum values of functions. In the centuries since Newton and Leibniz, calculus has become an essential tool in virtually every branch of science and engineering. It's used in physics to analyze motion and forces, in biology to model population growth, in economics to optimize production and analyze market behavior. In medicine, to understand the flow of blood or the spread of diseases, and in countless other fields. Modern technology, from smartphones to weather forecasting to space exploration, would be impossible without the mathematical foundation provided by calculus. It's really one of the most important intellectual developments in human history, which makes bitter dispute over its origin all the more ironic, I suppose. You know, I've been talking about Newton and Leibniz as if they were solely focused on mathematics, but both men had remarkably diverse interests and accomplishments. Newton, besides his work in mathematics and physics, was deeply interested in alchemy and theology. He actually wrote more on these subjects than he did on science and mathematics. He spent years studying biblical chronology and prophecy, trying to decode what he believed were hidden messages in the Bible. And his alchemical experiences were extensive. He was searching for the philosopher's stone and the elixir of life, like many educated men of his time. Oh, and Newton also had a rather significant career in public life. He served as warden and then master of the Royal Mint, where he oversaw a major coinage project and aggressively prosecuted counterfeiters. He was also a member of Parliament, though he apparently rarely spoke during sessions. And, of course, he was president of the Royal Society for the last 24 years of his life, which gave him enormous influence over British science. Leibniz was perhaps even more diverse in his interests. Besides mathematics, he made significant contributions to philosophy, developing a system known as monadology. He worked on logic, which was one of the pioneers of binary arithmetic, which is kind of the foundation of modern computing. He designed modern calculating machines that were quite advanced for their time. Leibniz was also active in politics and diplomacy. He served as a political advisor to several German princes and worked on reunifying the Catholic and Protestant churches. He advocated for the establishment of scientific academies across Europe and corresponded with hundreds of scholars and diplomats and aristocrats. So these were not just mathematical specialists. They were universal thinkers in the Renaissance tradition, interested in virtually all aspects of human knowledge. Their development of calculus was just one facet, albeit an extremely important one, of their intellectual lives. Let's return to the development of the notation systems for calculus, because I think this is a fascinating aspect of the story. Newton's notation, with dots placed over variables to indicate fluxions, was reasonably straightforward for simple cases, but became cumbersome when dealing with higher order derivatives or more complex functions. For instance, Newton would write the second derivative of x as x dot dot with two dots. But what about the derivative of a more complex expression, or a function of multiple variables? The notation didn't scale well to these more complicated situations. Leibniz's notation, on the other hand, was remarkably flexible. He would write the derivative of y with respect to x as dy by dx, which clearly shows which variable is being differentiated with respect to which other variable. Higher order derivatives could be written as d squared y by dx squared, d cubed y by dx cubed, and so on. For partial derivatives, that is, derivatives of functions with multiple variables, Leibniz's notation could be easily extended. If z is a function of both x and y, the partial derivative with respect to x could be written as partial z by partial x, using a different symbol to indicate that it's a partial rather than a total derivative. This partial symbol is a special cursive D used just for mathematics. This flexibility and clarity of Leibniz's notation is one of the main reasons it eventually won out over Newton's, even in England. Modern calculus textbooks almost exclusively use Leibniz's notation, with some additions and modifications that have been developed over the centuries. I find it somewhat poignant that Leibniz, whose contribution to calculus has been so enduring through his notation, died in relative obscurity and disfavor. His funeral was apparently attended by only his secretary. His grave remained unmarked for a long time. It's a sad end for someone who contributed so much to human knowledge. Newton, in contrast, had a state funeral and was buried in Westminster Abbey with great ceremony. His tomb is inscribed with the words, "Let mortals rejoice that there has existed such and so great an ornament of the human race." Quite the epitaph, isn't it? But history has a way of evening things out. While Newton's physical theories dominated science for centuries, it was Leibniz's approach to calculus that ultimately prevailed in mathematics. And in the 20th century, Leibniz's work in logic and binary arithmetic found new relevance with the development of computers and information theory. Sorry about that. Let's talk about some of the philosophical issues surrounding the development of calculus, because these were quite contentious at the time. Both Newton and Leibniz were working with concepts of infinitesimals, quantities that are infinitely small but not quite zero. This was mathematically useful but philosophically problematic. How can something be small enough to be treated as zero in some contexts, but not in others? The Irish philosopher George Berkeley famously criticized the aspect of calculus in a 1735 essay called The Analyst, subtitled "A Discourse Addressed to an Infidel Mathematician." Berkeley argued that the concept of infinitesimals was logically incoherent, and that calculus was built on shaky foundations. He had a point. The early development of calculus was more pragmatic than rigorous. It worked in practice, but the underlying concepts weren't defined with the precision that modern mathematics would demand. It wasn't until the 19th century that mathematicians like Augustin Louis Cauchy and Karl Weierstrass developed the concept of limits, which provided a more rigorous foundation for calculus without relying on the problematic concept of infinitesimals. In the limited approach, instead of saying that dy by dx is the ratio of infinitesimally small quantities, we say it's the limit of the ratio delta y by delta x as delta x approaches zero. This avoids the philosophical problems with infinitesimals while preserving the practical utility of calculus. Interestingly, in the 20th century, mathematicians developed non-standard analysis, which provides a rigorous foundation for working with infinitesimals after all. So, in a way, the original intuitions of Newton and Leibniz have been vindicated, albeit with much more mathematical sophistication than was available in their time. I mentioned earlier that the priority dispute between Newton and Leibniz had effects on the development of mathematics in England and continental Europe. Let me elaborate on that a bit. In continental Europe, particularly in France, Switzerland, and the German states, mathematicians readily adopted Leibniz's notation and approach. The Bernoulli brothers, Jakob and Johann, were early and enthusiastic proponents of Leibniz's calculus. They applied it to various problems in physics and mathematics and helped spread its use throughout Europe. Leonhard Euler, probably the most prolific mathematician in history, further developed and systematized calculus using Leibniz's approach. He applied it to a wide range of problems, from the study of curves to the analysis of infinite series to problems in mechanics and astronomy. In France, mathematicians like Guillaume de l'Hopital, who wrote the first calculus textbook, Pierre Verignon, and later Joseph-Louis Lagrange and Pierre-Simon Laplace built on Leibniz's foundation to develop powerful methods in mathematical analysis and its applications. In England, however, the loyalty to Newton and suspicion of foreign, particularly French and German, mathematics led to a relative isolation. English mathematicians continued to use Newton's notation and methods well into the 19th century, which made it harder for them to engage with the rapid developments occurring on the continent. It wasn't until the early 19th century that a group of mathematicians at Cambridge University, including Charles Babbage, who later designed the first mechanical computers, George Peacock, and John Herschel, formed the Analytical Society, with the explicit goal of importing the deism of Leibniz to replace the dotage of Newton. Yes, that pen is originally to them, not me. Their efforts gradually succeeded, and British mathematics began to reconnect with the continental tradition. But the delay had consequences. British mathematics and mathematical physics had fallen somewhat behind during the 18th century, and it took time to catch up. This whole episode is a fascinating example of how social and national factors can influence the development of something as apparently objective and universal as mathematics. Ideas don't exist in a vacuum. They're shaped by the social and cultural contexts in which they develop. Let's step back for a moment and consider the broader significance of calculus in the history of mathematics and science. Before calculus, mathematics was primarily concerned with static quantities, lengths, areas, volumes, and so on. Calculus introduced a systematic way to deal with change and motion, which opened up entirely new domains for mathematical analysis. It's hard to overstate how transformative this was. Suddenly, phenomena that had been difficult or impossible to analyze mathematically, like the motion of planets, the oscillation of pendulums, the flow of fluids, the propagation of waves, became accessible to precise mathematical treatment. This had profound implications, not just for mathematics, but for our understanding of the natural world. The laws of physics could now be expressed as mathematical equations, specifically differential equations, that captured how quantities change over time or in relation to each other. Newton's laws of motion and gravitation, for instance, can be expressed as differential equations that relate the acceleration of an object to the forces acting on it. Given these equations and suitable initial conditions, you can, in principle, calculate the future behavior of the system. This gave rise to a kind of scientific determinism, most famously expressed by Pierre-Simon Laplace, who suggested that if we knew the exact position and momentum of every particle in the universe and all the forces acting on them, we could predict the entire future and retrodict the entire past. Of course, we now know that this kind of perfect determinism is impossible, both practically, due to the complexity of the systems involved, and theoretically, due to quantum mechanics and chaos theory. But the basic idea that the physical world follows mathematical laws that can be expressed in the language of calculus has been incredibly fruitful for science. Before we wrap up, I want to mention a few things about how calculus is taught and learned today, because I know many of you might have had, let's say, mixed experiences with it in school. Calculus is typically introduced in high school or early college, with an emphasis on computational techniques. how to find derivatives and integrals of various functions, how to apply these techniques to specific problems, and so on. This approach has its merits. It's important to develop computational fluency, but it can sometimes obscure the big ideas and the historical development of calculus. Students might learn how to mechanically compute derivatives without fully understanding what a derivative represents or why anyone would want to compute one in the first place. I think there's something to be said for introducing calculus more conceptually and historically, understanding why Newton and Leibniz developed these methods, what problems they were trying to solve, and how they thought about concepts like infinitesimals can provide valuable context and motivation. Also, modern technology has changed how we learn and use calculus. Computer algebra systems can now perform most of the computational aspects of calculus automatically, which shifts the emphasis toward understanding concepts and knowing when and how to apply calculus in different situations. So, if you struggled with calculus in school, don't feel bad. It's a sophisticated set of ideas that took some of the greatest minds in history decades to fully work out. And the way it's traditionally taught doesn't always make its beauty and power accessible to everyone. Well, I think we've covered quite a lot of ground tonight. We've explored the development of calculus by Newton and Leibniz, the bitter priority dispute between them, the different notations and approaches they developed, and the broader impact of calculus on mathematics, science, and our understanding of the world. Calculus is one of those intellectual achievements that has transformed how we think about and interact with the world around us. From the technology we use every day to our understanding of the universe at its largest and smallest scales, the fingerprints of calculus are everywhere. And perhaps there is a lesson in the Newton-Leibniz controversy as well. Both men made invaluable contributions, and the mathematical community would have been better served by recognizing and celebrating both contributions rather than turning it into a nationalist dispute. Great ideas often emerge in multiple places around the same time, building on the collective knowledge and insights of the broader intellectual community. So the next time you hear someone mention derivatives or integrals, or you see a graph showing how something changes over time, or you use a device that was designed using principles of optimization, spare a thought for Newton and Leibniz and the remarkable mathematical tools they developed 3.5 centuries ago. Thank you for listening to Dormant Knowledge. If you're still awake and hearing my voice, I appreciate your attention. But if you drifted off to sleep somewhere along the way, which was partly the goal, then you won't hear me say this anyway. Either way, I hope some knowledge about the fascinating history of calculus has made its way into your consciousness, or perhaps your dreams. Until next time, this is Deb wishing you restful nights and curious days.